Okay, so hello Black Hat, and thank you for attending my talk. My name is Ben, and I'm here to present Lamphone, real-time passive sound recovery using light emitted from a hanging bulb. And I will start by introducing myself. I'm a computer scientist and a former Google employee. I'm a PhD student at Ben-Gurion University of the Negev and a researcher at Cyber at BGU. My research focus are privacy and security of IoT devices, and you can find or read more about my research at my website. This is a joint work co-authored by me, Yaron Pirotin, Professor Adi Shamir, Professor Yuval Alovich, and Dr. Boris Zadov, all of us from Ben-Gurion University and Weizmann Institute of Science. And this is the agenda for today. We will start by introducing the research question. We will then discuss the necessary background required to understand Lamphone. We will discuss Lamphone's threat model, bulbs as microphones. I will show you the evaluation from the experiments that we did. I will discuss potential improvements, takeaways, and questions and answers. Okay, so the primary question that we ask in this research is, can a hanging bulb be used as a microphone? And my answer to you is that by using scientific tools to analyze the vibrations of a hanging bulb, attackers can effectively recover high-quality speech and non-speech audio. Now, I will start with a warning. Turning a hanging light bulb into a microphone is a very challenging task, and probably some of you asking yourself why. The reason is that light bulbs were not exactly designed to be used as microphones, so during the next 35 minutes, I will do everything that I can in order to convince you that eavesdroppers can basically overcome this challenge if they know what to look for. Okay, so let's start to discuss about the necessary background to understand Lamphone, and we will start by discussing sound waves. Now, here are 3 interesting facts about sound wave. First of all, sound wave is basically air traveling through space, which its source can be some object that causes a vibration. For example, a person's vocal cords. And here is another interesting fact. Acoustic waves that have frequencies from around 20 hertz to 20 kilohertz can be heard by humans. Now, this actually leads us to discuss about eavesdropping. Now, according to Wikipedia, eavesdropping is the act of secretly recovering sound from a target or a victim without his consent. And eavesdropping comes in various forms. Eavesdropping can be performed digitally and physically, and in this talk we actually discuss about physical eavesdropping. Physical eavesdropping relies on objects that are located in physical proximity to the sound source. When a sound wave hits the surface of an object, it causes the object to vibrate, and by analyzing the object's response to sound, basically the vibrations, with a proper sensor, sound can be recovered. Now, this principle is being used by microphones, which are basically devices that are used to convert sound waves from to electrical signal using 3 primary components. The first component is a diaphragm, which is basically a thin piece of material that vibrates when it is struck by sound waves. The second component is a transducer, which is used to convert the vibrations to current. And the last component is A to D, which is used to digitize the analog electric signal to audio signal. Okay, so I want to discuss about eavesdropping related research, and I would mention that in recent years, the scientific community has suggested various ways to recover sound. All of these methods are basically can be categorized into one of the following categories. The first category is what I call the internal methods, and the second category is what I call the external method. So let's start to discuss about internal methods. And internal methods are basically methods that rely on data which obtained by a device located in proximity to a victim. In recent years, it was shown by scientists that motion sensors that are integrated to smartphones and speakers and vibration motors, again, all of which are integrated to smartphones. Data obtained from these devices can be used in order to eavesdrop sound. And in addition, even data obtained from magnetic hard drive can also be used in order to eavesdrop sound. Now, if I will have to summarize this section of internal methods, I would say that from the eavesdropper perspective, these methods are greatest disadvantage is that they are permissionless, which means that applications that implement these methods do not require any special permissions or permissions at all to obtain data from these devices. However, this method's greatest disadvantage is the fact that they require the attacker to compromise a device with a malware, and this in order to obtain data and to exfiltrate the data to his possess. Now, the second category of method is what I call the external methods, which are methods that rely on data obtained by a device that is not located near a victim. And probably the most commonly known method, or the most famous method, is laser microphone, which basically relies on a laser transceiver to recover sound by directing a laser beam at an object and analyzing the object response to sound. And laser microphone is a traditional method that is being used for years by eavesdroppers. And from the eavesdropper perspective, this method have two great advantages. The first one is that it is totally external, and it doesn't require, as a result, to compromise a device with a malware. And also, this method can be applied in real time. However, this method's greatest disadvantage is the fact that it is active, or what I call active method. The laser beam can be detected by victims or organization by using a dedicated optical sensor by detecting the laser beam that is being used, and which implies that a laser microphone is being used to eavesdrop sound. Okay, now, the second method in the category of external methods is the visual microphone. The visual microphone was suggested 6 years ago by a group of scientists from MIT. They suggested the use of a high-frequency video camera, which able to capture 2,000 frames per second in order to recover sound by analyzing the object's response to sound. And they were managed to show how a bag of chips can be used in order to achieve this goal by recovering speech from analyzing the vibration of a bag of chips. And from the eavesdropper perspective, this method is external as the method of a laser microphone. However, it has a great advantage of being passive, because no laser beam is involved in a visual microphone, making its detection very difficult for victims or organizations. This method's greatest disadvantage is the fact that it cannot be applied in real time, because this method requires heavy computational resources in order to process a lot of frames in order to recover sound, which, according to the authors, it takes a few hours to reconstruct a few seconds of sound. Now, if I will have to summarize this entire section of related work, I would say that each of the methods that were suggested over the years basically is limited in one of the following aspects. Some rely on remotely controlled device, which means that eavesdropper must compromise this device with a malware. Some methods are active, which makes it easier for the victim to detect the use of such methods. And some cannot be applied in real time because they require heavy computational resources, so none of these methods are perfect. Okay, so let's discuss about Lamphone's threat model. And in Lamphone's threat model, we actually assume that there is a hanging light bulb which exists in a target room. And we also assume that the sound in the room, which can be, by the way, the result of a conversation made in the room, creates fluctuations on the surface of the hanging bulb. And we also assume that there's an eavesdropper, an attacker, which basically directs an electro-optical sensor at the hanging bulb via a telescope. Now, electro-optical sensor is basically a sensor that converts light to voltage. And the optical signal that is sampled from the electro-optical sensor is digitized via A to D and processed using a dedicated sound recovery algorithm into an acoustic signal. We named it SND star in this case. Now, from an eavesdropper perspective, Lamphone's threat model actually is external, passive, and can be applied in real time, which means that it combines the advantages of laser microphone and visual microphones as well. Okay, so let us discuss about how light bulbs basically can be used as microphones and more specifically as diaphragms. And basically, as I mentioned before, as sound wave is basically air traveling through space, and the air causes a hanging light bulb to vibrate. It causes any object to vibrate and a hanging light bulb as well. However, a bulb's vibrations are so small that they are invisible to the human eye. So we started by asking ourselves, how small are these vibrations? And in order to answer this question, we conducted an experiment. We actually attached a gyroscope to the bottom of a hanging bulb. You can see it on the picture to the right. And we produced various sound waves at different volumes from nearby speakers. Again, you can see the speakers from on the picture to the right. And we sampled the gyroscope at 800 Hertz using Raspberry Pi 3. And these were the results that we actually that were obtained. We computed the angle as the function of the frequency. And when I say the frequency, it's basically the sine wave that was played for phi and for theta. You can see phi and theta in the scheme below. And we actually created these graphs for phi and for theta that are presented below. Now, by analyzing the results from the graphs, we actually we made three conclusions. The first conclusion is that the angle of vibration is very small. It's basically in millidegrees, as you can see in the graphs. The second conclusion is that the angle of vibrations is not equal. It changes as a function of the frequency. Again, you can see it on the graphs below. And unsurprisingly, the angle of vibration increases as the volume increases. Okay, now, based on the known formula of the spherical coordinate system, we actually computed the total movement of the hanging bulb, taking into account phi, theta, and the distance between the ceiling and the bottom of the hanging bulb. And we actually found that sound affected the hanging light bulb, causing it to vibrate at 300 microns between the analyzed spectrum. So, can we detect the movement of microns by using an electro-optical sensor? And in order to answer this question, we actually conducted another experiment. We actually directed an electro-optical sensor toward a hanging light bulb, as you can see in the picture to the right. And the electro-optical sensor is mounted to the telescope, to the white telescope on the right. And we measured the voltage that was produced by the electro-optical sensor from various distances, between 1 meter and 9.5 meters. Now, the graph presents the results that were obtained, and you can see that a different amount of voltage is produced by the electro-optical sensor when the sensor is placed 2 meters away from the light bulb, and when the sensor is placed 6 meters away from the light bulb. And again, this is not surprising because a different amount of light is captured by the electro-optical sensor. A bigger amount of light is captured by the electro-optical sensor when it is close to the light bulb. And however, we are actually interested in measuring small movements of the bulb rather than movements of the sensor. So how can the amount of light expected for displacement of 300 microns be computed? And we actually, using the results that were obtained from the previous experiment, we actually computed linear equations between two consecutive points on the graph. And you can see the linear equations below. And based on the linear equations, we actually computed the expected voltage resulting from displacement of 300 microns. And again, this is also presented on the table below. Now let's understand what can be learned from this table. And in order to understand, let us assume that we use a 16-bit A to D. And the 16-bit A to D provides a sensitivity of 300 microvolts. You can see the calculation in here. And analyzing this fact with respect to the table, it means that the sensitivity of a 16-bit A to D, which provides 300 microvolts sensitivity, it means that a sensitivity of 300 microvolts is sufficient to recover the entire spectrum that was analyzed in this case from a distance of between 2 and 3 meters, because the smallest vibration of 300 microns basically produces difference of 300 microvolts. So it means that we can actually recover the entire spectrum from a distance of 2.5 meters, for example. However, another conclusion that we actually made by analyzing this table is that in order to detect a bulb's vibration from 3 meters away, from a greater distance, from, for example, 4 meters away, the sensitivity of the system either needs to be increased or the signal obtained needs to be amplified. And later on, I will discuss how each of which can be each of these conditions can be satisfied. Okay, so we understand that the bulb is actually vibrating, but we ask ourselves, what exactly is vibrating? And in order to answer it, we actually obtained optical measurements via the electro-optical sensor when playing sine waves from the speakers in 2 scenarios. And the first scenario is with a diffuser covering the LED bulb. And the second scenario is without a diffuser covering the LED bulb. And we got these results. And you can see from the graph to the right is that the SNR decreases when a diffuser covers the light bulb. And the first conclusion we made is basically that the diaphragm is the light bulb itself and not the diffuser. It means that the light bulb is the object that is vibrating. And the second conclusion we made is basically that the diffuser decreases the signal-to-noise ratio due to the fact that it is basically aimed at distributing the light uniformly. Now, we ask ourselves another question: how uniform or how uniformly is the diffuser able to distribute the light across the light bulb? So, in order to answer it, we actually conduct another experiment where we obtained optical measurements via the electro-optical sensor when no sound was played near the light bulb from various angles. These were the results that were obtained, and as you can see, the diffuser doesn't distribute the light uniformly. Basically, the amount of light that is captured by the electro-optical sensor increases when the angle between the light bulb and the electro-optical sensor increases up to a vertical point which maximizes the amount of light that is captured by the electro-optical sensor. Again, all of which were done by fixing the distance between the light bulb and the sensor. We just changed the angle between them. And as a side note, I will say that if the diffuser was able to perfectly distribute the light uniformly, then we were unable to detect the small light changes that are the result of displacement of microns, and this is it. Okay, so the last experiment that we actually did is we tried to compare between various types of bulbs, and we did experiment where we compared the signal-to-noise ratio that obtained from 3 types of E27 light bulbs, the incandescent light bulb, the LED light bulb, and the fluorescent light bulb. And we found were the results that we obtained. And we found that sound could be reconstructed from every type of hanging light bulb that was examined. However, the signal-to-noise ratio of incandescent and LED light bulb is much higher than the SNR of the fluorescent bulbs. And this is due to the fact that fluorescent bulbs are able to distribute the light more uniformly than the other 2 types of bulbs that were examined. Okay, so we decided to evaluate Lamphone in real setup, not in a lab setup. And in order to do so, we actually evaluated Lamphone's performance for recovering sound from a bridge located 25 meters from an office. You can see the bridge on the picture to the left. And I would say that the office also contained a 12-watt E27 LED hanging light bulb. And let me show you the experimental setup. and afterwards you will see a video that was taken from where we actually conduct the experiment. Okay, so as you can see from the video, no sound that is played in the office can be heard from the bridge. There's an ambient sound which is the result of the rail station that is located below this pedestrian bridge. On the right corner, you can see how the light bulb is captured from the telescope. This is basically what the electro-optical sensor able to see or to capture when it is mounted to the telescope. And the first thing that we did is we tried to characterize the baseline, and we did it by conducting an experiment where we actually obtained optical measurements via the electro-optical sensor when no sound was played in the office. And this is the FFT graph of the optical measurements that were obtained. We actually got to two interesting results and conclusions. First of all, the LED bulb works at 100 Hertz. And as a result, there are peaks on the FFT graph at each of the harmonics of 200 Hertz, 300 Hertz, etc. And the first conclusion we made from this result is basically that we need to filter this noise with bandstop filters. Also, we found that there is noise at low frequencies which are below the 50 Hertz. They are boxed in red in this case. And this noise is the result of the location that we actually made the experiment. We put our equipment on a pedestrian bridge, which is located above a rail station. So there's a lot of noise of vibrations that actually they are the result of the bridge vibrating. And the second conclusion that we made from this result is basically that we need to filter this noise with a high-pass filter. Now, all of these conclusions are in order to isolate the audio signal from the optical signal without adding a lot of noise to the audio signal. Okay, now the second experiment that we did is we tried to analyze the frequency response, and we did it by obtaining optical measurements via the electro-optical sensor when a frequency scan was played via speakers in proximity to a hanging bulb. And this is the results that we actually got. Now, we actually did it with 3 types of telescopes, all of which have different size of lens. And the first conclusion that we made is that the signal-to-noise ratio basically improves when a telescope with a greater lens is used. I will explain later why this actually happens. And the second conclusion we made is that the signal-to-noise ratio is not equal across the spectrum. So an equalizer needs to be applied in order to balance the frequency response of the recovered signal. On the right side, you can see the equalizer that we designed based on the experiment that we did. Okay, now the next experiment that we did is we tried to recover non-speech audio. And we did it by, we played 2 famous songs inside the office, Let It Be by the Beatles and Clocks by Coldplay. And we obtained optical measurements and we recovered the signals. And these are the results visually. Opt of T is the raw data that was obtained from the optical measurements. S&D star is basically the recovered signal. And SND is the original signal. These are spectrograms of the signals that were obtained and recovered and played. And for many of you, it doesn't say a lot. So in order to convince you that this is actually a high quality signals, I will show you videos where we Shazammed the recovered signals, and I will show you that Shazam was able to accurately identify each one of them. Okay, now as you can see, Shazam was able to recognize each and every one of these songs. Also, SoundHound was able to do the same thing. And the next experiment that we did is we actually decided to recover speech audio. So we played the famous statement made by Donald Trump inside the office, "We will make America great again." Now we obtained the optical measurements and recovered the signals. And let me show you the results. Again, opt-of-t is the raw data. SND star is basically the recovered signal. And SND is the original signal that was played. We decided to investigate whether the recovered signal could be transcribed by Google's speech-to-text engine. Let me show you the results.
We will make America great again.
Okay, now as you can see, basically this is a high-quality recovered signal, which also, as you can see from the video below, Google's speech-to-text engine able to accurately identify each and every word of it. And bear in mind that Lamphone attack is capable of understanding President Trump, which is a very challenging task nowadays. Okay, so let us discuss about the potential improvements. And one potential improvement that can be used in order to optimize the quality of the recovered signal is using a telescope with a larger lens diameter. This is due to the fact that the amount of light that is captured by the telescope is a function of its lens area. And as a result, a bigger telescope with a bigger lens is able to capture a bigger amount of light. And as a result, the signal-to-noise ratio is actually optimized from this fact. And you can see it in the graph to the right. Okay, another potential improvement is optimizing the electro-optical sensor. You can do it either by using a better or more sensitive electro-optical sensor than the one that we used, or either by using multiple electro-optical sensor for multi-channel audio recovery, which is a common approach in audio processing. Okay, finally, you can also optimize the A2D, and you can do it by using an A2D with a lower noise level than the one that we used, or using a better A2D, 24 or 32-bit A2D instead of the 16-bit A2D that we used in our experiments. And also, I mentioned it briefly, but we actually used only standard techniques of audio processing, which involves basically bandstop filtering and high-pass filtering and some equalizer and some standard denoising techniques. Today, there are much more advanced filtering techniques to filter noise from the signal. For example, deep learning is an option. However, it comes with a cost. You will have to probably collect data in order to train such a model, and this is something that probably eavesdroppers would like to avoid. So again, the final optimization is come with some cost. Okay, so we are reaching to the end, and I intend to discuss about the main takeaway that I want you to take from this talk when you discussing about this research with your friends. And it is now 2020. However, I do believe that the year of 2026 is probably going to be a meaningful year in the life cycle or in the lifetime of Lanphone. And in order to explain you why, I suggest to examine Gyrophone's scientific progress. Now, for many of you, the name Gyrophone doesn't say a lot. However, in 2014, the attack of eavesdropping via motion sensor was revealed by a group of scientists from Stanford University. They named it Gyrophone. Basically, they showed that they can classify isolated words by obtaining data from Gyrophone that is integrated to each and every mobile phone nowadays. And they show a classification model that aims to classify isolated words that yields only results that only slight better than a random guess. Also, the attack vector back then relied on speech at high volume. And as a result, if I will have to somehow place gyrophone on the scale of practicality between not practical and highly practical, I would say the gyrophone is probably on 2014 is considered not practical at all. However, between 2015 and 2018, an increased understanding regarding this attack vector was gained, and the accuracy of the classification model was improved, and a better understanding regarding the experimental setup was gained, and some other studies even suggested the use of accelerometer instead of gyrophone, instead of gyroscope. And I would say that they actually optimize the practicality, so it will be somewhere in the middle between not practical and highly practical. And finally, on 2020, on NDSS, a group of scientists, I think they are from China, showed how the attack vector can be improved. So it is now, I believe, makes a real threat or real and practical threat to privacy. They show a classification model with the excellent accuracy. Also, the attack vector, they show how it can be relied at a normal volume of speech rather than high volume of speech, which basically they made the attack very practical nowadays. Now, my conclusion from analyzing this scientific progress is that it took 6 years to improve gyrophone to the point that it is now poses a real threat to privacy. And if I will have to say something regarding Lamphone now, so Lamphone is probably an evolution of visual microphone, and I believe that by making it able to satisfy, to work in real time, which is something that visual microphone didn't able to provide, we actually optimized the practicality to a place which is somewhere between, in the middle between not practical and highly practical. And I believe that during the next 6 years and by 2026, scientists will improve Lamphone, so it will also pose a real threat to privacy. You will probably gonna hear about another passionate PhD student that will come either to use Nick security or will present his work on DEF CON or at Black Hat or maybe even on security and privacy, and he will tell you, hi guys, remember the guys from Ben Gurion University that suggested Lamphone back then on 2020? I was able to now make it a real threat to privacy. I know how to convert light to sound at normal volume rather than in high volume. And this is the primary takeaway that I want you to take from this talk. Now, I want to thank you all for attending my talk, and if you will scan the QR code to the right, you will be able to get into the website that we made for Lanphone. This is probably a good time for me to take questions from the audience. Thank you once again. Okay, so I want to thank the audience for attending this talk and for the beautiful words that you actually wrote on the chat. Now, I want to address several questions that were raised by the audience. Imad asked, what is the distance, the effective distance that we were able to recover sound? So basically, you saw in the experiment, it was 25 meters. I think it was Zach that mentioned or asked how objects in the path of the electro-optical sensor influence the SNR. So basically, they are decreasing the SNR. But as you can see, we were able to recover sound through a curtain wall. So basically, they are decreasing the SNR, but you are still able to recover sound. Jared asked if the ambient sound near the sensor affects the recovery. So basically, the answer is no. You can see that the experiment where we placed our equipment on the bridge, and the bridge is located over a rail station, is very noisy, and it doesn't affect the recovered sound at all. Troy asked a very good question. What is the decibel level? So basically, when we did this experiment, it was a few months ago, maybe 3 months ago when we recorded this experiment. we use very high volume. It means around 100 decibels. And 3 months ago, this is what we were able to do. During the last 2 weeks, we were able to improve Lamphone to a level of 70 to 80 dBs, which is somehow a normal conversation, like the one that I'm just, the volume that I'm just using for this talk. And we did it, I hope to publish the paper soon, but we were able to do it using a desktop light bulb, and just by applying some magics to the obtained optical measurements. John asked, how is the directionality influenced? So it is very influenced. If the speaker won't direct its sound to the light bulb, so we won't be able to recover sound. But as long as there is somehow air that hits the surface of the light bulb, then you basically have a good chance to do things. How much the telescope costs? So this is what we call somehow telescopes for hobby. They cost several hundreds of dollars. You can buy them by yourself, probably in Walmart. Regarding speech from multiple people, this works as well. Again, it does not affect the way that sound should be recovered. And I think that this is it. I want to thank you so much for coming to this talk and attending my talk. And I hope you had great time. And you, again, can see some of our new progress in the website that if you will scan the QR code. Thank you so much.